Assalamualaikum and good day everyone. We will proceed with the final chapter for differential equation, which is partial differential equation. Okay, for this topic, okay, we will focus on the classification of PDE and also a method of separation of variables. So actually for this chapter, we will consider the analytical approach and also the numerical approach. But for this week, okay, these 2 weeks, okay, we have 4 weeks for chapter 5. So 2 weeks is for analytical method and another 2 weeks is for numerical approach. Okay. Alright, so this is the learning outcome. So at the end of this topic, you should be able to classify the types of PDE, define the terminology of PDE. So we have some terminologies which actually we have discussed this on chapter 1 previously. And the third is to solve the initial boundary problem of PDE by using the separation of variables method. Okay, so as an introduction, okay, PDE is a type of differential equation. So PDE are used to formulate and solve the problems involving functions of several variables, such as the propagation of sound or heat. Okay, and it is a differential equation which contains partial derivatives with respect to two or more independent variables. Okay, we have the PDE and also one is ODE. Okay, so we have ODE and PDE. Okay, PDE we have more than one independent variable. Okay, meanwhile for ODE we have only one independent variable. Okay, for example, we have as what we have discussed in chapter 2 and 3, which is the second order differential equation and also the Laplace transform. So we need to solve the second order differential equation where we have the solution later. Okay, when you apply appropriate methods, so you will have the answer as yx equal to an equation. Okay, so this is ODE. So but for ODE, we don't have the y prime y double prime, but you have the partial derivative. Okay, for example, you have del squared u del x squared plus del squared u del y squared minus del squared u del x del y equal to 0. So this is example of PDE where we have the partial derivatives here. This is partial derivatives, okay, where we differentiate u with respect to x partially. Okay. Alright. So there are few what we call examples of PDE, okay, which are Laplace equation. We have del squared u del x squared plus del squared u del y squared equal to 0. So this is considered as two-dimensional because we have x and y space. Okay, and then we have heat equation. Okay, heat equation, the independent variables are x and t, but this equation we considered as one-dimensional. Okay, and also the last is the wave equation. Okay, the equation is a squared del squared u del x squared equal to del squared u del t squared, and this also considered as one-dimensional. Okay, if you see the difference between one and two-dimensional is the variables. Okay, if it's involve t, so because t represent times, it's not represent the coordinate or the space. Okay, so that is why, since we have only x here, so that is why it's one-dimensional, 1D. Okay, but when it's involved two variables x, y, where x, y is represent the space, so that is why we say that this equation is in two-dimensional. Okay. Okay, these equations were modeled by its physical problems such as heat transfer problem, propagation of waves, and so on. Okay, and in further reading of this chapter, there will be a detailed discussion regarding the classification of PDE. Okay, determine the order of PDE. Okay, determine whether the PDE is linear or non-linear. Okay, determine whether the homogeneous or non-homogeneous. And also the last is the solution of the PDE, which by using the separation of variables method. Okay, so actually the order, linearity, and also the homogeneities is actually we have discussed previously on chapter 1. Okay, all right, so let's just look at what is the PDE. Okay, so a PDE is a differential equation which contains partial derivatives with respect to two or more independent variable. So for example, we have this. So sorry, I forgot to correct this one. So it's actually second order. So you have del squared u del x squared. Okay, and then we have del squared u del x squared. So these are actually the example of partial derivatives. This is not partial differential equation because if it's a PDE, means that it must have an equation. So this is just the partial derivatives. Okay, so partial differential equation is a differential which contains all the partial derivatives. Okay, all right. So a PDE is an equation which contains at least one partial derivatives. Okay, and the notation for PDE, okay, just now I used the del symbol here. Okay, del u del x, but actually we can also use, because some of the books also will use this kind of notation, ux. It means that if you have u subscript x, it means that we differentiate the equation u, okay, with respect to x, okay, partially. Okay, means that the other variable we will consider it as a constant. Okay, so this is we differentiate once. Okay, and if you differentiate twice, for example this one uxy, means that you differentiate respect to x first. Okay, we assume y as a constant, and then we differentiate the function where we have obtained the ux, we differentiate later with respect to y. Okay. Okay, now the first terminology is the order of the PDE. Okay, so order of a PDE defined as the highest order partial derivatives involved in the equation. Okay, so let's look at this example. Okay, state the order of the PDE below. Okay, we have the first equation, which is del u del y minus del u del x equal to x minus 2y. Okay, if you see from the equation, okay, on the left hand side, so the first term is a derivative of a partial derivative where we differentiate u with respect to y. Okay, so this is first order. So second term, we have del u del x, means that we differentiate u with respect to x partially. Okay, so this is first order. Okay, so the answer for A is first order PDE. Okay, second, we have del squared u del x squared plus del u del y plus u cubed. And we can see that this is the highest. Okay, and we know that this means that you differentiate u twice. Okay, that means this kind of equation is considered as second order PDE. Okay, C. Okay, we have del cube u del y del x squared. Okay, and the second term is del squared u del y squared. So second term we differentiate twice, but the first term we differentiate thrice, where we have we differentiate y with respect to y once, and we differentiate respect to x twice. So altogether is 3. Okay, 3 times that you need to differentiate the function. Okay, and therefore, okay, C is the third order. Okay, the last example. So if you have del squared u del y squared, so clearly here, this is a second order PDE. Okay, so maybe you can try this. Exercise 5.1, state the order of the PDE. So you can see A is 1, B is 3, C is 2, and D is 2. Okay, I will just focus on D. Okay, if you see the equation D here, okay, the first term is we have a derivative of u. Okay, we differentiate u with respect to y, and later on or we differentiate respect to x. Okay, or actually you can differentiate with x with respect to x first, and then you differentiate with respect to y. Okay, so this is second order. Okay, but here you have del squared, del u del x, and we have the power of 3. This does not mean that you differentiate the u 3 times. Okay, but you need to have only one differentiation. Okay, but that answers you need to multiply 3 times. Okay, so that is why this is to the power of 3. Therefore, this is not considered as third order. Okay, it's first order, but we multiply it 3 times. Okay, so the answer for D, that's why the answer for D is 2. Okay, the highest is 2. Okay, next we move to the linear and nonlinear terminology. Okay, again, so the PDE is said to be linear if all the partial derivatives are of the first degree and no products of dependent variables and derivative occur. Okay, it's just the same as what we have discussed in ODE. Okay, and a linear second order partial differential equation can be written in the form of this. Okay, we can write as this one. So we have this one as we differentiate u with respect to x twice, and then the coefficient for that is a, and then plus b, and then we have the derivation, the differentiation of u with respect to y and also x. Okay, this means that we have second order, and then plus c, so plus c del squared u del y squared, then plus d del u del x plus e del u del y plus fu equal to g. So this is the standard form. Okay, where the a, b, c, d, e, f, and g are the functions which contain only x, y, or constant. Okay, we cannot have u as the function of the a, b, c, d, e, and f and g, because if a is in terms of u, so it will becomes a nonlinear PDE. Or maybe you have cos u. Okay, so that will be a nonlinear. Okay, all right. Okay, so you also can write, okay, the standard form just now as this one: a uxx plus b uxy plus c uyy plus dux plus ey plus fu equal to g. So this is the standard or general form of second order partial differential equation. Okay, so we know that uxx just now is actually the same as del squared u del x squared, right? So our equation just now will becomes more simpler. Okay, it's simpler than the equation just now. Okay, and it's easy for you to see. Uxx means that you have the second derivatives, okay, or second order second order or second order partial derivatives. Okay, uxx, so this one uxy, this is uyy. Okay, so for actually this a b c d e f and a b c d e f and g, you need to apa nama to know and to remember the coefficient, because we will use all this abc in the next terminology. Okay, okay, so this is still in linear and non-linear. So let's look at the example. Okay, we have this one, del u del y plus del u del x equal to xy. So this considered as linear PDE because in front of the derivative there is just a constant one. So that is why we say that this function is, or this equation is linear. Okay, second, okay, we have the equation. The first term, the the coefficient for del squared u del x squared is 1. So it's okay. But the second term here, you have squared. So this considered as non-linear. Okay, because you have it's not in the form of linear. Okay, it becomes the quadratic lah. Okay. Next is del cube u del y del x squared. Okay, plus del squared u del y squared minus cos y. Okay, now we can see that the derivative, the coefficient for the derivative, the first term, this one is 1. Second term also the coefficient is 1. Okay, the third term, you don't have any derivatives. Okay, but since this is the function of y, so it's okay. Okay, because it is it's a function in terms of the independent variable. So we have the independent variables are x and y. So you can have any function, but make sure the function is in x and y only, so that we can call it as linear partial differential equation. Okay, so that is why the answer for C is linear. Okay, next is del u del t plus 6u del u del x plus del cube u over del x cube equal to 0. So the first term is 1. So it's constant, then it's okay. Okay, the second term we have 6u. Okay, so 6u is not in the form of x or y, or in this case x or x and t. Okay, it's u. It's the same as the dependent variable. So we cannot have this kind of equation in order to say that the equation is linear. So therefore, for D, okay, we say that the function or the equation is a non-linear PDE. Okay, why? It's because the product of the dependent variable u and the derivative. Okay, we have a combination of 6u and also the derivative of del u del x. Okay, all right. So next is exercise. Okay, in exercise 5.2, you just need to state whether the PDE is linear or not. Okay, if non-linear, you need to state the reason. Okay, the first is linear or non-linear. It's actually it's non-linear. Okay, because you have this one. It's a power of half. Okay, so it's non-linear. And then B, okay, B, the first term is okay, second term also okay, and third term you only have in terms of x, y, so it's linear. Okay, C, we have the coefficient for the derivative is C, it's just a constant, it's not U, so it's considered as linear. Okay, and the last equation is also linear. Okay, so only one which is non-linear. Okay, so we move to the next terminology, which is homogeneous and non-homogeneous equation, PDE. So it's very simple. It's just the same as ODE, where we will have, if you have the terms of u, okay, we put u on the left hand side. If you don't have the u, so you put it on the right hand side. And if g is 0, if on the right hand side is equal to 0, so we call it as the homogeneous PDE. Okay, otherwise, so we call it as non-homogeneous PDE. Okay, let's look at this example. Okay, we have all the equation on the left hand side involving u. Okay, so no need to rearrange, and we have on the right hand side is equal to 0. So this is homogeneous. Okay, so this one, okay, if you look at here, okay, all u is on the left hand side, and on the right hand side we don't have any u, so no need to rearrange the equation, and we see that the equation on the right hand side is not equal to 0, so this is non-homogeneous PDE. Okay, same as this one. Okay, even though you have the equation is equal to 0, but if you rearrange the equation, okay, and if you put only u on the left hand side, and this you don't have the term of u here, you just bring to the right hand side. So on the right hand side you have a function which is cos y, so that is why the those both equations is considered as non-homogeneous PDE. Okay, clear? Okay, so let's try this exercise. So you can try on your own this one. Okay, you have the answer there. So A is homogeneous, B non-homogeneous, C is homogeneous, and D is non-homogeneous. Okay, we can see that I will just show the non-homogeneous. Okay, here B, you can just bring the negative exponent xy to the right hand side, so it will become equal to exponent xy. So it's not equal to 0 anymore, so this is considered as non-homogeneous equation. Okay, alright, C. Okay, C here you have u. Okay, you have the derivative there, so you need to bring that del u del t to the right hand side, so to the left hand side, and therefore on the right hand side is equal to 0. Okay, and therefore we will consider C as the homogeneous PDE. Okay, alright, so for D is non-homogeneous clearly. Okay, so okay, now is the different terminology as in chapter 1, because this will focus on the PDE. Okay, so this is just the standard form of second order linear PDE, or we can write as A uxx plus b uxy, sorry, okay, plus c u uyy plus d ux plus e uy plus fu equal to 0. So this is homogeneous. Okay, so we can call the equation is hyperbolic, okay, if we can have b squared minus 4ac is greater than 0. If you have a positive value of b squared minus 4ac, so we call it as, the equation is called as hyperbolic. Okay, where to get the ABC there? So it's from the equation, the general form of or the standard form of a second order linear PDE. Okay, you have this one, A, B, and C. Okay, A is the coefficient for uxx, B the coefficient for uxy, and C is the coefficient for uyy. Okay, so you need to extract the values of A, B, and C, and then you solve for b squared minus 4ac. Okay, if you get the answer is positive, so the equation is hyperbolic. Okay, if you have the negative, if you have equal to 0, so it considered as a parabolic equation. Okay, and what happen if you get the answer for b squared minus 4ac as the negative numbers? So the equation is actually an elliptic equation. Okay, so you need to refer this. Okay, the idea is you need to solve for b squared minus 4ac. Okay, and from that answer, you can determine whether it's hyperbolic, parabolic, or elliptic. Okay, so you need to remember this. I'm not sure whether this kind of terminology will be covered in your final exam or not. Okay. Alright, so let's look at example. So this is the classification of PDE. So let's look at the first equation. We have del squared u del y squared plus del u del x equal to 0. Okay, so from here, if you compare, since we want to have only ABC, so we know that A is the coefficient for uxx, B is the coefficient for uxy, C is the coefficient for uyy. Okay, so we have the first term here is uyy. So we will have this one, we will have C equal to 1. And since we don't have uxx in this equation, so we will write as A equal to 0. Okay, and then B equal to 0 also, because we don't have the terms uxy. Okay, but C is equal to 1. And therefore, if you apply the formula b squared minus 4ac, okay, you will get 0. And since we have the value is 0, so therefore the equation is a parabolic equation. Okay, alright. Next is we have del squared u del x squared plus del squared u del y squared equal to 0. So again, if you refer to the coefficient, so uxx, we have the coefficient is A. Okay, uyy, it's uxy first. The coefficient is B, and if you have uyy, the coefficient is C. Okay, so this one you will have okay, A equal to 1, B equal to 0, and C equal to 1. Okay, because, and if you solve for b squared minus 4ac, okay, you will get negative 4. So negative 4 is less than 0, so it's considered as elliptic. Okay, alright. The last example for the classification. Okay, we have del squared u del x squared plus 3 del squared u del x del y plus del squared u del y squared equal to 0. So again, compare, you need to extract all the values of A, B, and C. Okay, where A you have 1, B you have 3, and C is equal to 1. And therefore, if you solve for b squared minus 4ac, you will get equal to 5. And since 5 is greater than 0, so we consider the PDE is the hyperbolic equation. Okay, it's a hyperbolic partial differential equation. Okay, alright, so you can try this exercise. Okay, you can try this exercise 5.4. Okay, we have this kind of equation. Okay, in the previous slide, we have Laplace, heat, and also wave equation. So use the formula b squared minus 4ac to determine or to classify the PDE, whether it's hyperbolic, elliptic, or parabolic. Okay, so you can maybe I will, okay, the first one is elliptic. Okay, clearly you can see that A is 1, B is 0, this one C is equal to 0. Okay, because it's not C equal to 0, but C equal to 1. Okay, so b squared minus 4ac, so you get negative numbers, so therefore it's an elliptic. Okay, so second, or heat equation, okay, we can see that A is equal to K. Okay, because the coefficient for uxx is k. So I just choose a equal to k, b 0, c also 0. So b squared minus 4ac I think I will put here. Okay, b squared minus 4ac is equal to, we have 0 minus 4 minus a, which is equal to 0, and then c is k. So we get the value is equal to 0, and since it's equal to 0, so this is a parabolic equation. Okay, the last exercise. Okay, we have the equation a squared del squared u. This is a wave equation over del x squared equal to del squared u del t squared. Okay, you need to extract all the values of a, b, c. Okay, from here you will have a equal to what? A square. Okay, because we have this equation. Okay, what is b? Okay, b, a just now is uxx, b is uxy, c is uyy. Okay, if you have the equation in terms of x and t, so a must be for coefficient for uxx, b is uxt, and c is utt. Okay, just change the y to t. Okay, so back to this equation, right? So we have this equation. We can see that from here b is equal to 0. Okay, and what is c? Okay, c is the derivative of the coefficient for utt. We have this utt, and the coefficient is 1. But if you see carefully, so actually this is equal to del squared u del t. So you need to bring this del squared u del t to the left hand side. So the equation will becomes minus del squared u over del t squared equal to 0. And from here we can have c is equal to negative 1. Okay, so if you have c is equal to negative 1, and we have a equal to a squared, b equal to 0. So if you solve for b squared minus 4ac, so you will get 0 minus 4. Our a is a squared, and c is negative 1. So you will have what is the answer? 4a squared. Okay, we know that if you have a squared, the value always be a positive numbers. Okay, a squared always give a positive value. Okay, if you have a squared, okay, if your a is negative 2, so a squared is equal to positive 4. Okay, any values of a, but if you have a squared, so the answer will becomes positive. So that is why for a squared must always equal to greater than 0. It must be positive value. And since it's greater than 0, so we consider c as the hyperbolic equation. Okay, so that is all for the first part. Okay, the first part is just a terminology. So second part, I will give the solution for a PDE. Okay, for the general PDE by using a method of separation of variables. Okay, so see you again on the next video.